Alright guys, we're going to go ahead and take a look at our universal law of gravity quiz. And we're just going to look at a few questions on it because we already did the other questions in another video. So let's take a look at our first question here. And this question says, the planet Gallifrey, however you want to pronounce that, has 2 times the gravitational field strength and 2 times the radius of the Earth. So this sounds important and this sounds important. One's talking about the radius and one's talking about the gravitational field strength. In other words, A, right? Now let's look at what it's asking us to do here. It says, by what factor does the mass of this planet compare with the mass of the Earth? So because they're giving us this information up here telling us that the gravitational field strength is 2 times that of Earth and the radius is 2 times that of Earth, we can just answer this in relation to the factor of what it will be in comparison to Earth. So to do that, let's go ahead and write down our equation. Acceleration, or gravitational field strength, is equal to big G times m over r squared. And again, because this is a factor type question, we don't actually need the values of these in here. We don't need to know what the mass of the Earth is or the radius of the Earth to figure this out. So what I recommend you do is that we look at this equation and we just manipulate our values. If it's 2 times as big, we plug in 2 for that value. If it's 2 times as big for the radius, we plug in 2 there. Anything that's not getting manipulated can just stay as itself, meaning that we'll just plug 1 in for that number. So let's go ahead and do that. The gravitational field strength is 2 times as big, so I'm going to plug in 2 for A. And then the gravitational constant is always G, so that can just be 1. The mass is what I'm trying to figure out, so I'm going to leave that variable as m. And then the radius is now 2 times as big. We can't forget, though, that it's radius squared in this equation. Now we just go ahead and solve for that variable m. We get 2 is equal to m over 4. Solve for m, we multiply 4 over, and find out that the mass of this planet has to be 8 times the mass of the Earth in order for this to make sense. So I'll go ahead and write that here, saying mass of planet is 8 times the mass of the Earth. All right, and then there's our first problem. Let's go ahead and look at our next one. So the next one now has a planet called planet Beta, and for this one, our gravitational field strength is still 2 times as big, but now our mass is what's being manipulated, and we're going to double that mass. We want to figure out what the radius of this planet is compared to the radius of the Earth. So let's go ahead and do the same thing we did before. Write our equation down, A equals G times m over r squared. Next, we're going to go ahead and plug in these values. Gravitational field strength is talking about acceleration here, so plug in 2 there. G is just a constant, so we can just leave that as 1. And then m is now 2 times as big, so I'm going to plug in 2 there. And r, well, r is actually unknown, so I'm going to leave it as r. Now I'm going to go ahead and simplify this. I find out that 2 is just equal to 2 over r squared. To get r squared by itself, I can go ahead and multiply the r squared over if I want. I'll really take the long route here. I get 2r squared equals 2, and then I'm going to have to divide 2 from each side. I find out that r squared is equal to 1. Square root both sides, and we find out that r is just equal to 1. What does this mean? Well, this is going to tell us that the radius of planet Beta is the same as the radius of the Earth. Now let's take a look at another type of problem, and this one we're actually going to end up solving for stuff. So we're going to go ahead and use some numbers other than just 1 and 2, and we're going to figure out what the force of gravity is between you and the person that you are sitting next to. All right, so imagine you're sitting next to somebody right now, and you measure that distance to be about 0.5 meters away. So first thing I want to do is just list these variables. I see that I have a mass right here. I'm going to go ahead and call that mass 1. And say that mass 1 is 60 kilograms. Next, I have another variable here. I'm going to go ahead and list this as mass 2. And again, it doesn't matter which one we assign mass 1 or which one we assign to mass 2. I could switch these around if I wanted to. It's not going to make a difference. Next thing I notice is that it tells me that we're sitting 0.5 meters away. So my R in this case is going to be 0.5 meters. And then obviously we know that our G is just a constant, so that's 6.67 e to the negative 11th. What I want to do now is go ahead and write my equation. So I have Fg is equal to big G times m1 times m2 all over r squared. And I know that I need this equation because it's asking me to calculate the force of gravity. And this is my force of gravity equation when I am solving between two objects that have mass. But we have our equation and we've listed all of our variables. All we have to do is plug in. So we get Fg is equal to G, which we said was 6.67 e to the negative 11th, times m1, 60, times m2, 80, all divided by r squared, which is 0.5, and then squared. Do some math, and we end up getting a force of gravity that should be equal to 1.28 e to the negative 6 newtons. And you're going to notice that this number is extremely small, right? E to the negative 6, that's a very, very tiny force of gravity, which makes sense because the two masses are you and another person. And if you think about it, this is the force of gravity, or the force of that gravitational pull that you're going to feel towards each other. If you are just sitting down next to somebody, do you feel like you're going to fly off your chair towards them? No, right? And that's because this value is so tiny that it's not really going to have any impact on you. But let's say that if you were really far away, maybe in distant space, and this person was this close to you, yeah, I mean, you might actually start drifting towards them because there's very little external forces that are pulling you left to right. The reason why we're not going to drift towards that other person also is because we're on Earth, and Earth's gravitational pull is so much bigger that it's just going to override this value. All right, let's take a look at our last problem. It says, let's assume that the moon is about to crash into the Earth. Oh no, right? Run, hurry up, grab your phone, all the things that are valuable to you. In other words, their surfaces are touching. Ooh, interesting. At this instant, what is the force gravity between the two objects? Well, we're going to need to do some math to figure that out and also label some variables. So I went ahead and I put a picture in here for you guys. So here's our moon and here's our Earth. Okay, so we can see that the center of the moon is right here and the center of the Earth is right here. I've given you some values, right? I told you what the radius of the Earth is. So from here to here, we know that this value is 6.378 e to the third kilometers. We want to go ahead and convert this to meters. So I'm going to say e to the 6 multiplied by 1,000 meters. And then same thing for the moon. Here's my moon's radius. Okay, so from the center to the outer edge. And that one's 1.74 e to the third, again, kilometers. But we know that we want meters, so it's e to the 6 meters. There's a reason why I gave you the radiuses, and we're going to talk about it in just a sec. So this question is asking us to figure out the force of gravity between these two objects. We know that force gravity is equal to big G times m1 times m2 all over r squared. We know that these are our two masses, so we can just go ahead and start labeling some of this information. So mass 1 I can say is the mass of the Earth, and that value is just right here in my table, 5.98 e to the 24th kilograms. I don't need to change anything about it. That's the units that I need. M2 is the mass of the moon, and that's 7.35 e to the 22nd kilograms. And we can see that the mass of the moon is a lot smaller than the mass of the Earth. Well, we know why, right? That's because the moon is made out of cheese. And then if we look at the R value here, this is where things get interesting. So R, if we remember, is the distance from one center to the other. So the center of the moon is here and the center of the Earth is here. So we need this distance. Well, if you look really closely, that's the radius of the moon plus the radius of the Earth. So this one's just radius of Earth plus radius of moon. So we just need to go ahead and add these two values together to figure that out. And I went ahead and did that for you guys. And I found out that the distance from the center of the moon to the center of the earth, assuming that they're about to crash into each other, is 8.118 e to the 6 meters. And then lastly, we know that our equation needs big G, and big G is just a constant, so it's always the same value, 6.67 e to the negative 11. Now we just need to go ahead and take all these numbers and plug it into our equation. So we find out that Fg is equal to G, which is 6.67 e to the negative 11th times M1, 5.98 e to the 24th times M2, 7.35 e to the 22nd. Let's put parentheses around the entire top part of our fraction, divided by r squared. Well, r we said is 8.118 e to the 6 squared. Now we just go ahead and plug that into our calculator and it spits out our answer. We find out that the force of gravity between the moon and the earth, assuming that they're about to crash into each other, is going to be 4.45 e to the 23rd newtons.